Hello, good morning everyone. Once again, welcome to the world of electronics. Our lesson for today is all about SMPS or switch mode power supply. Unlike linear power supply, switch mode power supply is an electronic power supply that incorporates a switching regulator to convert efficiently the electrical power into its highest density, excellent voltage regulation, and excellent temperature stability. Hence, switch mode power supply is widely used in electronics technology today. The electronic products like the power supply of the satellite TV receiver, the power supply of the DVD player, the power supply of the Devant LED TV receiver, the cell phone battery charger, and the laptop battery chargers are just among the 99% application of switch mode power supply. The circuit that we have here is a complete circuit diagram of SMPS or switch mode power supply, which is almost identical with the power supply unit that we have here. So, we will be using this power supply unit here to explain further the behavior of the switch mode power supply circuit. Actually, or basically, the switch mode power supply circuit is composed of two circuits. These are the hot circuit over here and the cold circuit over here. If we have to examine closely the actual power supply board of this DVD player, you can notice at the solder side of this power supply unit that there is division between the two circuits. We have here the brown color. We have here the cold circuit, and the hot circuit is over here. Also with this power supply unit over here of this Devant LED TV receiver, at the bottom side, you can notice that there is a gap between these two circuits, and it is labeled with hot and cold. So, what are these hot and cold circuit? This circuit here is called hot because it processes higher amount of voltages ranging from 100 volt up to 350 volts. Whereas the cold circuit processes a lower amount of voltages ranging from 2 volts probably up to 40 volts. Actually, the two circuits is isolated or separated with this electronic device, the so-called optocoupler. So what is this optocoupler and how does it work in the circuit will be explained in detail in part 4. For this time, our discussion will be at the hot circuit. Part 4 will be the cold circuit. So in the hot circuit, we have to emphasize the operation of the electromagnetic interference circuit, the bridge rectifier circuit, the control IC circuit, the snubber circuit, the switch mode transformer or the high frequency transformer. Also, we have to include also this optocoupler. So, we will study them thoroughly to understand the behavior of the circuit. So, let us start from the first stage we have here. This is actually the actual board of the circuit here. We have here the AC cord composing of the switch and the AC cord for the outlet. Actually, the two connectors can be interchanged It can be removed from the circuit board, and you can even interchange the connection. So there is no rest here. It is just a switch and an AC source. So it is somewhere here. You can connect the switch here, and the AC source is over here, and other terminal is over here. So there is 3 terminals over here: the switch and the AC source. So how does it work? So if we are going to measure the voltage at the outlet, so again we'll set this to AC voltmeter. Press this one here so that you can see the AC symbol, and measure the voltage at the outlet. Okay, that is 234 volts. 234 volts. Okay, the 234 volts, once it is connected into the circuit, the current will be pushed by the 230 volts around the circuit, and each of the components will drop voltage, and we call them potential difference caused by the flow of the current. So during the entrance of the current from the voltage, there is a so-called circuit protection device and the EMI filter network. At first, it passes the fuse, which serves as a protector or circuit protection circuit. Whenever there's a large amount of current here, this fuse will blow to protect the circuit from damages. Or anything that there is overloading here, there is higher resistance at the load, this fuse will blow to limit the number of damages, of course. Then we have here the thermistor. What is the purpose of this thermistor? We call this one as NTC. NTC, or negative temperature coefficient. Actually, there are 2 types of thermistor. We have the NTC and the PTC. NTC again is negative temperature coefficient, and the other one is positive temperature coefficient. Thermistor in general is an electronic device that resistance varies in accordance with temperature. So the purpose of this thermistor is to protect the circuit, especially this IC, which is sensitive to variation of voltage or surge current or excessive amount of current that flows over here caused by the current from the outlet. So at first, it slows down the entrance of the current little by little until it reaches to 5 seconds. So let us measure how the thermistor behaves. Okay, we have here an NTC. Actually, we have lots of NTC here. We have here NTC 8D11. Then we have also here NTC 5D11. So what is this 5D11? NTC again is negative temperature coefficient. 5 here is 5 ohms. Then D is diameter. 11 is the millimeter. So the diameter size of this thermistor is around 11 millimeter. Then the resistance is 5 ohms. Just like this one, this is 8 ohms, 11 millimeter again, then 8 ohms. D there is the diameter. So NTC, negative temperature coefficient. So we have to measure using ohmmeter. So we will use analog multimeter. Set this one to adjust the serum adjuster. Okay. Okay, we have here. Let us try to measure the resistance of this resistor. Okay, we will connect this one here because NTC thermistor is non-polarized. We have here. Okay. The resistance actually is 8 ohms. 8 ohms, no? 0 ohms is over here, then 10 ohms. So, that is the resistance when the TV receiver is turned off. But, once it is turned on, the current flows. The resistance will usually change because thermistor resistance will vary in accordance with temperature. Okay. It is during cold condition. It is 8 ohms because 8D11. 8 ohms, diameter is 11. So, observe closely the deflection pointer. Once the current flows, naturally the thermistor will become hot. And the resistance there is getting lower. No, it is getting lower. See? It is getting lower until it reaches to 0 ohm. That is actually the characteristic of this thermistor. Meaning, negative temperature coefficient. During cold condition, the resistance is 8 ohms. But when it becomes hot, due to the flow of the electric current from the outlet, the resistance little by little will become 0 ohm. So that is the characteristic of the NTC, negative temperature coefficient. The resistance will be getting lower as soon as it is heated by the flow of the electric current. Okay? Okay. Unlike PTC, there's another application of that PTC because when the resistance, when the thermistor becomes hot, the resistance there is getting higher. No? It is actually applied in a certain circuit such as automatic degaussing coil. So that will be explained later on. Okay? So, in this TV receiver actually, of the Devant TV receiver, there is a so-called thermistor, NTC, we have here. No? So, another type of NTC with different resistance. So, that is really the operation of the NTC. Meaning to say, it protects the circuit from the excessive amount of current. There should be no abrupt entry of the current. So, dapat dahan-dahan lang ang pagpasok ng kuryente. Dahan-dahanin lang. Pero masasaktan kapag biglaan ang pagpasok ng kuryente na masyadong mataas. So, it should be controlled by the NTC. So, naturally, the thermistor will become hot due to the flow of the current, but it delays the entry of that higher amount of current. At first, higher resistance 8 ohms will oppose the surge current until it becomes 0. Full swing amount of current will come in. Okay? Then, we have here the EMI interference, or we call it electromagnetic interference, or EMI filter network. It is composed of this one, the toroidal inductor, and this capacitor, metallized polypropylene capacitor, polypropylene film capacitor, metallized polypropylene film capacitor, together with the inductor, will constitute as a low-pass filter. So, it goes like this, class. Okay. Okay, we have here the thermistor, and we have here the capacitor, the resistor also here, and we have here the inductor. Okay. It goes like this, class. Usually, the woofer speaker of the sound system, to reinforce the low frequency response ranging from 20 Hz to 100 Hz, there should be a low pass filter to be fed to the woofer speaker in such a way that it ensures that only low frequency will be fed to the woofer speaker. So, filter out any high frequency and passing the low frequency. What is allowed to pass here actually is the discharge frequency, which is 60 Hz. 60 Hz. Any frequencies beyond 60 Hz. For example, we have here the AC waveform. That is now actually the 60 Hz. But if it is accompanied with high frequency that may create noise to the circuit, will be eliminated by means of this EMI filter network. It goes like this. No more noises. What is the origin of that noises or electromagnetic interference? For example, the vibration of the transformer of that post installed in the Solico post. There is a very big transformer there. It is prone to variation actually. That is the reason why the voltage at the outlet is varying always. Varying 234, 233, 235, 234.5. It varies the voltage for every now and then. It is caused by the vibration of the transformer. There are usually noises there around 1 kHz, 2 kHz, 3 kHz caused by those noises. Especially the welding machine, from the nearby. Okay. They may cause electromagnetic interference. This should be filtered out by this low pass filter network. Okay? We have here actually the capacitor, which is the yellow one. No? The yellow one here. Okay? Then, it is fed to the bridge rectifier circuit we have here. There are 4 rectifier diodes over here, connected in bridge configuration. Their purpose is to convert AC. They will convert AC into DC. This AC, as it passes the rectifier diodes or rectifier circuits, it becomes like this. Okay? From 6 Hz, positive, 0, negative, becomes 0, positive. However, the frequency doubles. It becomes 120 Hz. We have already studied that one during the part 2. We are now actually in part 3. No? Okay? Actually, the output at this rectifier circuit is already DC. It is already DC. However, it is pulsating DC. In a certain amplifier, once you apply this voltage, pulsating DC, to a sound amplifier circuit, the music actually being processed by that audio amplifier is always accompanied with hum. And that is now the 120 Hz. And the variation of the voltage is also here. Probably this is 300 or 230, 150, 230, 150. There is a bigger variation of voltage that may cause hum. No? Since 120 Hz is within the audio frequency range, because the audio frequency range which are audible to the human ears are ranging from 20 Hz to 20 kHz. Then 120 Hz is within that audio frequency range. However, they are heard as hum, just like that, accompanying the sound or the music. However, that is eliminated with the use of supply filter. We have heard the supply filter capacitor that smooth out the pulsation. So, that pulsating DC, once it passes the 100 microfarad, 400 volts, it becomes like this. Okay? However, the voltage is increased. The voltage is increased right at this one. So, okay, let us connect this one to the outlet and measure the voltage is stored in this capacitor. Okay. We have here. Let us try to measure the voltage across that capacitor using digital voltmeter. It is DC actually, so we'll set it to DC by pressing the select button. Then be careful. Again and again, you cannot be electrified under this cold circuit. Only this hot circuit. You can be electrified. You can feel an intense feeling, intense pain. Okay? Let us measure the voltage across this capacitor. Actually, it is around 323 volts. But here, the AC volts actually is around, the AC volts is 236 volts. But the voltage across capacitor is 324 volts. You might be amazed how come it reached to 324 volts, because it goes like this. The voltage was at the outlet is 236 volts. Okay. That 236 volts at the outlet is just 70.7%. 70.7% of the 100% amplitude. It is just the RMS, which is measurable by our tester. But the peak value can be obtained by means of this capacitor, because this capacitor doesn't only smooth out the pulsation to make it varying DC, but it also stores the voltage up to the peak value, which is 100%. So peak value equals RMS times 1.414. So the RMS there is 236 volts times 1.414 is, okay, 236 times 1.414 is equal to 333. 333. But here, it is DC across this capacitor. 323. 323. So it is actually reduced. Why? Because diodes, there are 4 diodes. 2 diodes will conduct at the same time. Each diode will drop 0.7 as a biasing voltage of that diode. 0.7 and 0.7 volts for the 2 diodes will drop 1.4. Plus the load over here will also drop a smaller amount of voltage. That becomes 234 volts, no? Or what was that? Across this capacitor, 336 volts, okay? Okay, so it is proven now that this capacitor will store voltage up to the peak value. Aside from smoothing out the pulsation, the voltage is increased up to the peak value. Okay. Now, there is a snubber circuit. What is that snubber? Snubber. Okay. Snubber circuit is snubber circuit composing of a resistor, a capacitor, and a diode. So we have actually here. So let us first disconnect this one, so that we cannot be electrified. So we have here the 56 kilo ohms, this capacitor, and this diode. These are the three components that are connected to neutralize the voltage spike. Actually, the voltage around this switch mode transformer, which is here at the primary winding, this is now actually the high frequency transformer or the switch mode transformer. So the amount of the voltage that is across this winding is around 336 volts stored by this capacitor here. So, okay, we have here. Actually, the operation of this control IC, because in this control IC, there is a so-called oscillator. There is an oscillator here. This voltage, 336 across this winding, will be turned on, turned off, turned on, turned off. It is actually done by this oscillator here. So what is that? What is that oscillator? So it goes like this, class. It goes like this. So where is our Okay, it goes like this, class. This is now the primary winding of this high frequency transformer. Then we have here the the MOSFET or the metal oxide semiconductor field effect transistor. We have here the drain, we have here the source, and we have here the gate. We have here the voltage across here. Of course, from this capacitor, there is an amount of 336 volts present right across this inductor. However, it goes like this. This transistor is a switching transistor, which is built in at this IC. So we have here actually the IC. That IC is a control IC. Okay. There is a built-in switching transistor there, which is the MOSFET. Okay. So the gate of the MOSFET is actually supplied with pulsating, or we call it pulses. No? Pulses derived from this stage here. It is actually a pulse generator. Pulse generator. Generated by this pulse generator. It is actually, we can exemplify the circuit here. This one here. Okay. Let us supply this with a power supply. Okay. We have here the positive side. Then, connect it to the positive of the battery. Then, the negative here. Negative, positive. Negative, positive. Okay, let us wait for a while. Push. Okay. It goes like this, class. Right in this IC, control IC, there is a so-called pulse generator. It goes like this, class. So, we can actually see the signal. What kind of signal is that? So, we can connect it here. Then, to the negative side. To the negative side here. And we can see the Okay. Okay, it goes like this, class. This is now the pulse being generated by this pulse generator. And it is present right at the gate of the switching transistor. So, if we are going to measure the voltage across it using this DC voltmeter, we have here the negative side and the positive side. Okay, let us measure the voltage outputted by that. Okay, maybe here. The positive side of the voltmeter is connected to the pin 3 of that IC, the stable multivibrator LM555, and this is connected to the negative side of the circuit. So it goes like this, class. Okay? Okay? When it is turned on, at this point here, it is 6 volts, 0 volt, 6 volts, 0 volt, 6 volt, 0 volt. When it is turned on, 6 volts. When it is turned off, 0 volt. Okay? It goes like this, class. Oh, it goes like that, class. So, the output signal goes like this. It is rectangular wave or square wave. These are the pulses outputted by this pulse generator using LM555 as a stable multivibrator that generates these pulses. If it is 8 Hz, we can actually measure the frequency there using this digital, where is our digital multimeter? We have here digital multimeter. Okay, we have here. We can actually measure the frequency here. Set this to Hertz to measure the frequency. So, how much would the frequency outputted by this? We have to connect the positive side to the pin 3, and the negative side is over here. The frequency is 3.5. Okay, 2 Hertz. We can increase actually the frequency here to the maximum level. It is 5 Hertz. The faster blink, the higher the frequency. Okay, it goes like that, class. It goes like this. Oh, okay. 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 Anyway, the frequency tester is no longer connected here. Now it goes like that. On, off, on, off, on, off, on, off. So these are the pulses outputted by this pulse generator, and it is actually located in this IC, no? Which turn on and off the switching transistor here. So it goes like this. So when 5 volts is right at the gate, so the resistance between drain and source is very low. There's a large amount of current circulating here. This 336 volts will be transformed in the secondary, because if this is fixed DC, cannot be transformed to the secondary. So the 336 volts should be turned on, off, turn on, off, on, off, on, off, in such a way that there is variation of magnetic field here, just like a traditional ignition system of a vehicle. There is a battery, the 12 volts here. There is a battery there, 12 volts. Ignition switch. We have here the ignition coil. We have here a switch, cavity switch with capacitor across it. Then it goes like that, class. Then we have here the spark plug. Spark plug. There are 4 spark plug for the 1342. Okay? So when it is turned on, the ignition switch is turned on, current will flow across this coil. So the switch here is turned on, turn off, turn on, turn off because there is a starting motor there that rotate the assembly of this ignition coil. On off, meaning to say the voltage there is positive 12, 0, positive 12, 0. So it must be turned on and off in such a way that this transformer could transform the voltage. Actually, the voltage 12 volts is transformed to a higher amount of voltage, around 10,000 volts right across this spark plug. So there is a spark here between the two metals of the spark plug, which will ignite the compressed air fuel inside the cylinder. Inside the cylinder, there is a piston there that moves up and down to compress the air fuel mixture. So when it is moved on top, there is a very high pressure because the air and the fuel there are compressed. So that's the time that the spark plug will ignite. Then there is combustion. It pulls down the piston. The piston is connected to the connecting rod, to the opening well, connected to the well. That's why the well rotates due to the movement of the piston inside here. So this is the situation of the ignition switch. So in such a way that there is transformation of voltage here. So the 12 volts battery should be on off by means of the switch being moved by the starting motor. Okay, it goes like that. So there is actually two power stages here. Conversion of AC into DC. Then this DC again will be converted into DC, which is a lower amount of DC voltages. So there is actually frequency here. That is why the switch mode transformer is also called high frequency transformer. The frequencies that is used by the circuit is ranging from 10 kilohertz to 1 megahertz. So that depends upon the circuit actually. No? Okay. That's all for today, class, because the time is almost longer. Thank you very much. Let us wait for the part 4. Okay. Thank you.